So welcome everyone. Today we will dive into two fundamental concepts in linear algebra, eigenvectors and eigenvalues. These ideas are crucial not only in pure mathematics but also in many applied fields, including machine learning, physics and economics. By the end of this session, you will have a basic understanding of what eigenvectors and eigenvalues are, now how they relate to matrices, and why are they important. So what are eigenvectors and eigenvalues? They come from the study of matrices. An eigenvector is a vector that does not change its direction when a matrix or linear transformation is applied to it, but it may stretch or shrink. The eigenvalue represents how much the eigenvector is stretched or shrunk. The core equation is AV is equal to lambda V, where A is the matrix, V is the eigenvector, and lambda is the eigenvalue. So how are we going to geometrically interpret these two eigenvectors and eigenvalues? So to start with, visually imagine a vector undergoing a transformation. In most cases, the vector changes both its direction and length. But for an eigenvector, only the length changes. It either stretches or shrinks. But the eigenvalue tells us by how much. This makes eigenvectors incredibly useful for simplifying complex transformations. Now coming to the calculation part of it. How are we going to calculate eigenvalues? So the first step is finding eigenvalues involves solving a special equation called the characteristic equation. We first subtract lambda I, where I is the identity matrix, from A, and then take the determinant. We set this determinant equal to 0 and solve for the eigenvalue limit. And finally, the roots of this equation are the eigenvalues. So coming to the calculation of eigenvectors. Once the eigenvalues are known, finding the corresponding eigenvector is a matter of plugging each eigenvalue lambda back into the equation A minus lambda I times V is equal to 0. Solving this equation gives us the eigenvector. Each eigenvalue will typically have one or more corresponding eigenvectors. Finally, let's walk through a concrete example with the matrix A, where first row consists of values 4 and 1 and the second row consists of values 2 and 3. We'll start by finding the characteristic equation, then solve for the eigenvalues, and finally find the corresponding eigenvectors. This slide illustrates the step-by-step process we have just discussed. So eigenvectors and eigenvalues have a wide range of applications. In data science, they are used in principal component analysis (PCA) to reduce the dimensionality of data. In physics, they help analyze the stability of systems. And in engineering, they are key to understanding vibrations in structures. Economists use them to model systems with multiple interacting variables. Their practical utility makes them a critical tool in various fields. So to wrap up, we have learned that eigenvectors are special vectors that maintain their direction after a transformation. While eigenvalues tells us by how much they are scaled, and we have also seen the equation that defines the relationship with matrices and explored the applications across various domains. Thank you for your attention, and I hope this gives you a solid introduction to the concept of eigenvectors and eigenvalues. Thank you very much.